So this talk is going to be about pan privacy, and specifically, we're going to argue that it is a model of differential privacy that sits between the central and local models for both privacy and utility. And for this talk, we will mostly focus on the difference between pan and local privacy. So we'll start with some basics of local privacy. In words, in local privacy, there's going to be a distributed database, and users are going to keep their own individual data points. There's going to be a protocol that learns about the data through public communication with users. And the way users are going to participate in this communication is to send responses through randomizers. And randomizers are going to be differentially private functions of a single data point. So in pictures, you've got these individual data holders on the left. Each one of them produces some noisy output using the randomizer. The noise guarantees their privacy, and the learner looks at these noisy outputs to come to some conclusion and learn something. We're going to talk about a specific type of locally private protocol known as a sequentially interactive protocol, where each user is going to speak at most once. So they will produce at most one output. But the advantage of sequential interaction is they can do so in multiple rounds. So the third person to speak gets to see the outputs of the first two people. So there is an adaptive quality in sequentially interactive protocols. So in math, we'll say a sequentially interactive protocol A is epsilon delta locally private if all of its randomizers, so the randomizer that each user employs to produce an output, it's an epsilon delta randomizer. So it satisfies this kind of relationship where the output distribution given input x is very similar to the output distribution given input x prime. That's why it's private. So pan privacy, which was originally defined by Dwork, Nauer, Potassi, Rothblum, and Yetinen, is a very different model. In pan privacy, the data is going to arrive in a stream, one element at a time. So now the algorithm actually gets to see the input data. And what it's going to do is the algorithm will see the element, update its internal state, and then continue processing the stream. So the adversary in this model gets to see one of these internal states in the final output, and the view must be a differentially private function of the stream. So relative to the local model, pan privacy is easier because the algorithm actually gets to see raw data. But relative to the central model, pan privacy is harder. It's a stronger privacy guarantee because the algorithm has to maintain this differentially private intermediate state. So in pictures, you got some data, the algorithm sees it, and while seeing it, it maintains a noisy state to keep track of what it's seeing. So in math, we say streams S and S prime are neighbors if they differ in at most one element. And then we say a protocol is pan-private if, for all neighboring streams, anytime t, at any subset of the input and output space, this relationship holds. So a little more clearly, what is this saying? It's saying that if the adversary sees one internal state and then one output, and then the output at the end of the stream, that joint distribution to satisfy epsilon delta differential privacy. So why should we study this model? We'll argue that if the user of the trusty operator today, the differential privacy of the intermediate state, plus the post-processing guarantee of differential privacy protects the user against future intrusions. So for example, if the user is worried that, say, the government will subpoena the algorithm operator, or that the person who owns the pan-private algorithm operator changes, what happens is that because the operator was using a pan-private algorithm, when they saw the user's data, they processed it and produced this differentially private summary. And this differentially private summary, that internal state, is the only thing the operator keeps around. And because of the post-processing guarantee of differential privacy, once they've gotten to the point where the differentially private state is the only thing kept around, the user's privacy is guaranteed forever. So that is why in pan privacy, the way the trust that the user has for the operator today is really the key point. And so we have this cartoon graph. In the central model, the user needs to trust the operator both today and in the future. The PAN model gives a little more privacy. The user only needs to trust the operator today and not necessarily tomorrow. And finally, in the local model, the user doesn't need to trust the operator at all. But as we see on the left-hand side, there is a decreasing utility as a price to pay for the increasing privacy. So the first question we can ask is, okay, we have this one intrusion assumption in the definition. How necessary is this assumption? The first result we show is that this assumption is necessary. Specifically, any pan-private algorithm, any epsilon pan-private algorithm against multiple intrusions can be converted into an identical, sequentially interactive epsilon locally private protocol. So if you need pan-privacy against multiple intrusions, if you have a multiple intrusion pan-private algorithm, then you have a locally private equivalent. So really, the single intrusion pan-privacy is the only game in town. If it's multiple intrusions, then it becomes a completely different model. It becomes local privacy. So the way this works, in the local to pan direction, it's pretty simple. You just run the locally private protocol and maintain its transcript as your pan-private algorithm's internal state. So because it's a locally private protocol that you started with, that transcript is always going to be a differentially private function of the data so far. So not only is this pan-private algorithm that just simulates the local protocol pan-private against two intrusions, and it's pan-private against an arbitrary number of intrusions. It can maintain this transcript as like a public object and still be pan-private. So that's one direction, the easy direction. The other direction, converting a multi-intrusion pan-private algorithm to a locally private one, is a little bit more complicated. But intuitively, if you have an adversary that can see two internal states of the pan-private algorithm, in particular, they can look at states t and t plus 1 for any t. So if the algorithm fails to randomize its state between time t and t plus 1, the adversary can do this kind of diff attack where they diff the two states and recover the element that was seen in the middle. So to protect against this attack, the pan-private algorithm has to randomize between every internal state. So it has to randomize from 1 to 2, 2 to 3, 3 to 4, etc. And this state-by-state randomization sounds like sequential local privacy. And really, the proof relies very heavily on that idea. So with that result in hand, we can ask, well, how meaningful is single intrusion pan-privacy? We suggest that it's still a useful object because, as we just saw, single intrusion pan-privacy suffers when a user contributes data between intrusions. So if a user adds their data between two parts of a diff attack, that is when they will lose privacy. So that means that users are most worried about giving data to an operator that's already been compromised. But this suggests that the relevant parameter here is the user's trust in the operator today. Because if the user trusts that the operator today has not been compromised, then by the post-processing guarantee we already talked about, single intrusion pan-privacy protects them against any future events and is strictly more private than central privacy. And so this case where the user trusts the operator today, but maybe not tomorrow, separates pan-privacy from both the local model and the central model. So this brings us to our second result about pan-private uniformity testing. So in uniformity testing, an algorithm is going to receive samples from some unknown distribution P over a discrete domain of size K. And the task is to distinguish the case where P is uniform over K from the case where it's alpha far from uniform in total variation distance from the uniform distribution. So distinguish the case where it's a uniform distribution or it's very non-uniform or sufficiently non-uniform. And you want to do this with some non-negligible probability, say at least 2/3. So the nice thing about this problem of uniformity testing is that it's well studied under other privacy models. For example, in the second line, ignoring the dependence on like alpha and epsilon, the dependence for the central model in that second line is root K. Samples are necessary and sufficient. Then at the bottom, you can see that for non-interactive local privacy, which is a more restrictive form of local privacy where not only does each user only speak once, but there's only one round in which everyone talks. In that form of local privacy, we can see at the bottom that K samples are necessary and sufficient. So for this work, the thing we prove is that for pan privacy, K to the 2/3 samples are necessary and sufficient. So it neatly sits in between the central and local sample complexities. And along the way, we extend the previous non-interactive sample complexity lower bound to the sequentially interactive case as well. This is the full version of our upper and lower bounds. You can see they differ in this last term by this root epsilon quantity, but are otherwise technical. So the sketch for the upper bound is, well, the main idea is to split the difference between the central and local approaches that we just saw. So for example, many of these central approaches use some variant of a fine statistic. So for example, you might compute the following statistic. You sum over the K domain elements of the observed count of each element I and all the samples you took. And then you subtract off the expected count under the uniform distribution. So here we took M samples. So if it's uniform, we expect to see M over K of each of the K elements. Then you skew it by some squaring to notice departures from uniformity. And then that's your statistic. So if we wanted to do this under pan privacy, the only additional requirement is to add noise to each count HI in order to achieve pan privacy. And if you do this, you actually get a non-trivial guarantee. You get a protocol that requires K to the 3/4 samples. But maybe we can do better. So at the other end of the spectrum, the local approach, what they do is they randomly halve the domain and reduce the problem to uniformity testing over a domain of size 2, which is distinguishing Bernoulli distributions. So say you started with a domain of size 6, halving the domain, you end up with something like this. So what you've done is now you view samples of 2, 3, or 6 as from the first element, and the remaining samples as from the second element of some fictional 2-element distribution. So this is good because you've reduced to a small response domain, size 2. That's good for local privacy, but you've sacrificed a bunch of testing distance. You can see like here, this looks like a very non-uniform distribution, but this is a much less non-uniform distribution. In fact, more formally, your testing distance goes from like alpha to alpha over root K. So if you use the strategy under pan privacy, you end up using around K samples. So that's even worse than the K to the 3/4 we saw from adapting the central approach. So maybe we can split the difference between these two things. The central problem is that we track so many things, we maintain so many counters that we have to add noise to each one to be pan-private. So we add a lot of noise. There's too much noise for our signal. At the other end of the spectrum, in the local approach, we track too few counts. We only track 2 of them. So now there's not that much noise, but we're actually losing a bunch of signal. So we want to trade off better between this noise and signal. So what we'll do is, instead of partitioning the domain into 2 groups, we'll partition it into n. And now we'll uniformity test over this domain of size n. So for example, if n was 3, we would go from 6 things to 3 things. And now this actually looks fairly non-uniform. It's not as non-uniform as it was before, but it still looks pretty non-uniform. Specifically, we showed that if you partition the domain into n groups, the testing distance change is alpha to alpha root n over k. So you pick some n carefully to trade off noise from using a coarse distribution and from using a too fine distribution. So you pick n to trade these 2 things off. Specifically, you pick the n given here, and that's how you get this upper bound. Our lower bound, I'll just say that we adapt an information theoretic lower bound for uniformity testing under memory restrictions. And the main contribution is replacing this memory restriction with a privacy restriction. So the takeaway is pan privacy is appropriate when the user trusts the algorithm operator today, but perhaps not tomorrow. Pan-privacy against multiple intrusions is equivalent to sequentially interactive local privacy. And pan-privacy against one intrusion trades off both utility and privacy between the central and local models. Central was root k samples, pan is k to the 2/3, and local is k. Some open questions, there are the straightforward ones of closing the gap on our bounds. There is also no known fully interactive locally private lower bound. We can also ask, well, all the results we proved are for epsilon pan privacy, pure pan privacy. It's not clear what the case is for approximate pan privacy. And finally, there is recent work that connects pan privacy and robust shuffle privacy. Specifically, it turns out that for certain problems, including uniformity testing, you can use pan private lower bounds to prove robust shuffle private lower bounds. And in fact, there is no known problem that separates robust shuffle privacy and pan privacy. So either separating the two models or proving some more general connection is an interesting open direction as well. Thank you.